Welcome to this presentation, another presentation in the line of our Introduction to Compressible Flow. In this one, working with the governing differential equations to come up with some very interesting relationships of the terms that we'll regularly deal with when working with compressible flow. All right, so first of all, we're going to start with the mass flow rate. This should be hopefully familiar to you. So m dot is equal to the density times area times velocity of a flow. And for going through thing about our diffuser, this is going to be constant and not changing with time. Now, if we look at the differential form of the mass flow rate, what that would turn into is we would say d of differential over density times area times velocity is going to be equal to 0. Right? If this is actually constant. And therefore, the actual differential breaks out to a, the area times velocity, d times the change in density, the derivative of the density times area times the change in velocity, plus density times velocity times d area, differential of the area, all equal to 0. So that's all expanded out there. All right, and if we divide through by rho AV, what we end up with is actually our conservation of mass in differential form, which is the derivative of our density over density plus the derivative of the area over area, and the derivative of the velocity over velocity. All right, and that's all equal to 0. All right, so that's one relationship that we're going to use, so from the conservation of mass. Now let's look at the energy balance. So if we take the energy rate balance, which we did before, or a previous presentation we did it, so that was our H2 plus V2 squared over 2 plus, equals our H1 plus V1 squared over 2. All right, and that equals our, or let me say just H plus our V squared over 2, and that'll equal some constant. All right, the differential form of that comes to be just our dH is equal to minus V dV, V being our velocity. And if we combine it with the differential form of entropy, which I'm not going to show you here, there's a discussion in different books that you can look at for that. But we come up with our conservation of energy in, again, differential form. Now, being careful here that the conservation energy, and this is dP, so change pressure over density, plus the velocity times dV, again, of the velocity equals 0. Now, the assumption here is, and hopefully this looks familiar from Bernoulli, except that we've made the assumptions here that we're going to ignore the potential energy and we're ignoring heat loss and work. All right, so that's what we have with the conservation of energy equation as well as our conservation of mass equation. If we combine the conservation of mass relation and we substitute in our speed of sound relation, or at least the differential form of that, what we'd end up with is this relationship here, where we have the change in area over area is equal to the change in pressure over density times velocity squared, 1 plus the Mach number squared. Now, let's look at this because there's a lot of interesting relationships we can get out of this. The area is always going to be a positive value, density is going to be a positive value, and velocity is going to be a positive value. Now, what's going to be happening here that's very interesting is this Mach number, because it's 1 minus the Mach number. So it matters when our Mach number is greater than or less than 1, how it affects dP and A. All right, so let's look at first Mach number less than 1. If Mach number is less than 1, then this is going to be a positive value over here. All right, so I'll just put a positive here in parentheses to indicate this parenthesis here is going to be a positive value. That means that if dA is, if it's a positive change, so going up, there's going to be a positive change in the pressure. But if there's a negative change in the area, then there'll be a negative change in the pressure. So those correspond. Likewise, if the Mach number is greater than 1, now we're going to have a negative value, all right, in the parentheses. And so therefore, area and the pressure are going to be different than each other, right? Because if we have a negative value here, we're going to need a negative value from our dP in order to get a positive value on the right-hand side with a positive value there. So if A goes up and the Mach number is greater than 1, then the pressure needs to come down. And if the area goes down, then the pressure needs to go up. All right, so that's one relationship that we want to consider. Now the next one, if we then substitute the conservation energy, the differential form that we used on the previous slide, into this equation up here. So to go from here to here, we're going to substitute in the conservation of energy. And now we're going to relate our area to velocity. And again, area is going to be a positive value. Velocity is going to be a positive value. And now we're going to look at this Mach number. So again, starting with Mach number less than 1. So again, what that means, we're going to have a positive value in the parentheses. All right. Well, we got this negative sign here now. We got to be careful with it. Okay. So if we're positive in here, that means the velocity is going to have an inverse relationship with the area. All right. So that means if the area goes up, the velocity goes down. And if the area is going down, that means the velocity would go up. All right. If the Mach number is greater than 1, then we'll have a negative value in the parentheses. And now we'll have a similar relationship where area goes up, velocity goes up. And if area goes down, velocity goes down. All right. So what does that really mean? I mean, that's kind of cool, and okay, we've got some relationships here. Let's look at a visual of what's happening here. Specifically, we're going to look at this second equation and see how this one relates visually here. All right, so remember this relationship. If we're less than 1, if Mach number is less than 1, then as area goes up, velocity needs to go down. So it's inverse relationship for less than 1, and it's a concurrent relationship if we're greater than 1. So let's start with the less than 1 piece. All right, so here's our equation again. And we have these two scenarios. So you have the scenario over here when we're less than 1. And so we said if we're less than 1, Mach number is less than 1, then we have the inverse relationship. So what's happening here? If the area is going down, then velocity must be going up. So if the area is going down and the velocity is going up, what is this shape? What's a term for this shape? Likewise, over here, if the Mach number is greater than 1, Mach number is greater than 1, we have a, the relationship is good because now we've got a negative value over here. And that takes out this negative. So now if area goes up, velocity goes up. Right? So in both these cases, the velocity is increasing as it goes through here. So those two are nozzles. All right, and maybe by process of elimination, guess what these two are, but let's go back here. So Mach number less than 1. Mach number is less than 1. Then if the area goes down, the velocity goes up. All right, and if the, I'm sorry, whoops, here's Mach number less than 1, I'm sorry. So Mach number, if Mach number is less than 1 and the area goes up, velocity goes down. And over here, we're supersonic, so if m is greater than 1, so that means area and velocity have a similar relationship. So area goes down, velocity goes down. So those are diffusers. All right. So what we find is if we're subsonic, this is what we're familiar with. All right. This is a nozzle, right? The velocity goes up in this case, and for the diffuser, velocity goes down. What we have now is with compressible flow, things kind of change on us, so that if the area goes up for a supersonic flow, your velocity can actually continue to increase. And over here, if we actually have a nozzle type shape, right, that we're used to calling a nozzle, this is actually a diffuser. It actually works to slow down Mach numbers that are greater than 1. Right? It's a supersonic diffuser. Right? So that's what we can see between these two relationships. All right? So one of the things I want to look at here is what if we have a scenario like this? So you have a converging nozzle. And so this would say if we're a subsonic flow coming in, right, and we go through this nozzle, that means the velocity is going up. And it's going to be here at the throat, say we get to the point where it's sonic. That means the Mach number is equal to 1. Well, it's only at this area A here. But what if we said, hey, what if we made this area smaller? What if we went from A to B, and B, the area at B, was less than the area at A? Would the Mach number go up? Would the Mach number be greater than sonic? Well, it wouldn't, because if we go back here, to this case, the only way the velocity can continue to increase in a supersonic Mach number is greater than 1, we have to go to a expanding type shape. All right. So if we want the velocity to go up at all after we're to the point where we've reached a sonic point where Mach number is equal to 1, it has to be a converging nozzle at that point. We cannot continue to narrow it down and thinking that the Mach number is going to increase in that way. All right, so a little bit non-intuitive there, but I think a very interesting result. All right, so we're going to talk more about what kind of scenarios we can have going through a nozzle, but that'll be in the next video. So I sure hope you stick around for that one.